So, welcome to our talk. We are very happy to be here at sunny San Diego, or not so sunny today, but yeah. So, we're here to talk about the security of copying out and inside two containers. There have been, in the past few years, many vulnerabilities in copy implementations for many different container engines. And we find it might be a great opportunity to come here and discuss the different vulnerabilities that we saw and what we can do for the future. So myself, I'm Ariel Zelivansky, and this is Yuval Avrahami.
Hi, guys.
We work for Palo Alto Networks, previously at a small company called Twistlock, where we have a security research team where we try to find bugs in the cloud-native environment and runtimes and programs that are used in cloud-native environments. So we have a bunch of TVs we found. We disclose everything, write some articles about what we find, basically trying to make cloud-native more secure for everybody. And through that, the last 2 years that we've looked into existing vulnerabilities and some that we've found, we saw that CP is actually some place where there have been too many vulnerabilities for something that is supposed to be very simple. So with that, the agenda for today, we're going to start with some background about both containers and the CP command, how it is used, who uses it, and what's the purpose of it, basically. And then we'll just dig into some of the vulnerabilities we've seen that we think are most important and interesting for us to learn from. We look at Podman, Docker, and finally Kubernetes, which had some of the worst CP vulnerabilities in it. And we'll end with some takeaways, basically what we think may be the best approach to implementing CP from scratch now that we've learned so much from different vulnerabilities. Oh.
So can you guys hear me? Yep. So let's start by talking about containers. So as most of you probably know, containers are restricted processes rooted to a separate file system. But I think the best way to really understand what it means is to see how you start a container. So let's see how Docker starts a container. So Docker uses runc, which is the industry standard tool for all the low-level stuff we have actually running the container. And it spawns a helper process called runc init. And what runc init does is start building the container around itself. So it enables several isolation features supported in the kernel that you probably heard about, like namespaces, cgroups. It routes to the image file system, which for Docker is at this path, and does all sorts of other things. And then once it enabled all of those restrictions, it is isolated enough from the host to be considered a container. And then the final thing that runc init does is exec the binary that you ask for. So if you ran docker run ubuntu sleep, it will exec sleep. And the result is exactly what you asked for, a container running the binary that you asked for in the file system of the image that you specified. So those are like containers in 60 seconds or less.
So most of you in this room have probably heard the term container engine or container runtime. And the difference between these two is not always very clear. So let's pause at that for a second and distinguish the difference between them. So container runtime is basically everything Yuval just described. It is the program that actually uses the kernel to create containers. You can run containers with it or execute processes inside containers with it. But it doesn't give you all the juice that we actually like about containers. It doesn't let you manage images. It doesn't let you connect to a remote repository or basically just manage the containers running on your system, see what is running, and run complex commands upon these containers that you have. So this is container engines. We have many different implementations for container engines, including Docker, CRIO, and Podman. They give us all the commands that allow us to build images and also copy from running containers. So for that reason, we have so many different implementations for the copy command, because it's implemented at the engine level and not at the runtime level. Each engine it implements this command differently. So you have a CP command for Docker, for Podman, and for LXD, and this is all different implementations, and they take a different approach for how to actually make the copy operation. And Kubernetes in itself also implements the copy command by itself, even though it is not a container. So what is the copy command? It's probably what you imagine it to be. Copy files from a container to your computer, or from your computer to a container, or you can even copy from different running containers. And the syntax is similar to the Unix cp command that you may be familiar with, so it's not all that complicated. And the use case is actually more common than we've originally thought, because it is used by many developers and DevOps for production environments to either debug containers and see what's going on with them, deliver some files into them, or it's used in some scripts to manage containers. We've seen copy actually being used in the wild. So it is relevant as for that you can see that it has been implemented in almost all the container engines have an implementation for the cp command. So you can guess that it is useful and people are making use of this command. So having vulnerabilities is actually highly relevant. And in the past few years, we've seen a surge in vulnerabilities being disclosed and some information being disclosed about them. But we even saw some CP vulnerabilities being found as back as when container even started at around 2014. When Docker was implementing this command, there were some issues, some security bugs, and that you can find and see that they've had issues that could have been exploited. So it is not a new concept, but in the last few years, many more people have taken interest into finding this kind of vulnerabilities, including our team. And with that, let's just dig into the vulnerabilities and see the actual implementations issues.
So let's start with podman. So that's the podman cp command. It's pretty simple. That's how you copy a host file to a path of the container, dir abc. And let's see how podman actually implements this. So the first thing podman does is build the container path, but from the host view. So it takes the container mount point on the host and adds it the path that you ask for in the container. And then it does something that is quite similar to a normal Unix cp command using that path. So that's pretty straightforward. What could go wrong here? Well, symlinks. So this is the first CV we'll talk about today. And the problem was that symlinks in podman were resolved under the host root. So let's look at an example. Let's say we have an attacker-controlled container, which has a symlink inside it called fake dir. And then a podman user does something like podman cp host file to a path that contains this symlink. What will happen is the symlink will be resolved under the host root, and the file will end up actually in the host file system and not inside the container. So that's bad. It isn't that easy to exploit because you need to know where the user tries to copy to, but you don't want to have a command where files could pop up on the host file system. So that's not good. And let's see how Docker deals with it. So now we're talking about copying in Docker. So how Docker did it to deal with this problem, it will first resolve the container path under the container root. Only then it will take that resolved path and add it to the container mount point on the host. And finally, it will copy. So the same example, we have a symlink inside the container, and we try to copy some file to a path that contains this symlink, now using Docker. So the first thing Docker does, it resolves the path. So we resolved it, and only then we add it to the container mount point on the host. And finally, we copy. So that seems to solve the problem because the symlinks are resolved before the copy occurs, but it actually didn't. And that leads us to our second CV, where in Docker we could have a symlink exchange attack, a race attack. And let's illustrate that with an example. So let's say we have a completely normal cp command, copy a normal file from the host to a normal directory sumdir on the container. So what will happen? Docker will try to resolve the path in the container. It's a normal directory, a normal path, so it stays the same. Then it will add it to the container mount point. And finally, it will copy. So that seems good. But the problem was that if an attacker managed to take one of the components in the path, in the container, and switch it to a symlink between stage 2 and 3, we'll have a race attack where the file will still end up on the host file system. So that's quite annoying, and you can see that symlinks cause a lot of problems when copying to and from containers. But what can we do? What other solutions are there to deal with that? So one solution that was used is to sort of partially enter the container. And what that means is that the container engine will fork and run a helper binary that helper process will partially enter the container, which normally meant root into the container file system, and then it will read all of the files that you requested in the container while being rooted to the container. So all symlinks are resolved under the container root, and you have no symlinks that can point to the host. So let's see how Docker implemented this solution. Now we're talking about copying out. So the Docker daemon forks and runs a helper process called Docker tar. Docker tar then roots to the container. It tars the requested files inside the container, and then it passes back the resulted tar file to the Docker daemon, and there are no symlinks issues because it accesses the files while being rooted to the container. Cool. So this seems like a very good solution. What could go wrong here? Some stuff. Well, you are partially entering the container, and what that means is that the helper process is sort of creating a bridge between the container and the host. So Docker tar, the helper process, is partially inside the container, right? It's rooted to it, but in some aspects, it is still inside the host. It is in the host namespaces, C groups, and so on. So it could create a bridge between the container and the host. And that's exactly what happened in the worst CPCV in all container engines so far, and one of the worst CVEs in Docker up until now, where you will have a full host compromise whenever you copied out files out of the container. The attacker didn't need to know when you were copying or from where you are copying. Whenever you copied out of an attacker-controlled container, it will gain root code execution on the host. So that's bad. So what happened? So as we've said, Docker tar roots to the container, right? And Docker is written in Go. Specifically, that version was in version 1.11. And that version has some feature, or you might call it a bug, where some packages, some Go packages that had embedded C code inside them would dynamically load shared libraries at runtime. So what would happen is Docker tar would root to the container file system, and then will dynamically load several libraries from the container file system. Those were specifically several libnss libraries. So to clarify, you have a process which is only rooted, not completely isolated, which loads and executes code which is controlled by the container. That is a host compromise. So the attack scenario for this vulnerability is a Docker user that copies files out of the container, which is either run in a malicious image, where we have a malicious libnss library, or if an attacker compromised a running container and replaced the libnss libraries. So with that, let's see a POC for this vulnerability. Can you guys see or is it? Yeah? Cool. So what I did here is create an image with my own version of the libnss library. And what this library does is once it is loaded to a process, it executes a binary at path breakout. That's all. So when Docker tar will load this library, it will execute a binary at path breakout/breakout in the container. So if that's not so clear, wait a few seconds and it will be a bit clearer. So let's run the image. Cool. So we have the container running. And now let's copy some files from the container. This is, by the way, the vulnerable Docker version. So let's copy out some logs, for example. Oh, I called it. Sorry about that. Cool. So what I did with the breakout binary here, it just sleeps. That's all it does. So we can see what's going on inside with the copying. So let's look at the process tree. Cool. So we can see that the Docker daemon actually spawned the Docker tar helper binary. And because it loaded our malicious library from the container, it executed the breakout binary. And the breakout binary, as I said, all it does is sleep, so we can see the process tree. So let's inspect a bit closely, or more closely, the Docker tar. So it is process PID. Cool. And if we look at the root, We can see that it is indeed rooted to the container, like we expect. And we can also see, if we cut its credentials, that it is privileged. So this bit mask means full privileges. As a comparison inside the container, you have less privileges. Some bits are turned off. So we can see that now that we better understand what's going on, let's run. Oh, we need to just kill the sleeping process. Cool. So now that we understand what's going on, let's run another image. And in this image, what I did is just replace the breakout binary. And what it does is mount the host file system to the container at path hostfs. So let's see that in action. Cool. And then when we copy out any file, so for example, let's copy out bin bash. Doesn't really matter. So let's see if our breakout binary ran. And we can see that it did, and a new directory called hostfs was created. And if we look inside, we can see the entire host file system, and the container had full access to it. So we can do something like then if we look at the host, you can see that the container can actually do whatever it wants. Thank you. Cool. So that's pretty bad. So how did they fix this? So what did they do? What they do is that they alter the init function of the Docker tar process so that it will call just random functions from the problematic Go packages to force it to load the libraries, the libnss libraries, in the init phase before it's rooted to the container. So now they will be loaded from the host file system. And aside from that, I'm pretty sure that in current versions of Go, they fixed this issue. So Go doesn't no longer loads certain libraries at runtime. So we can see that even this solution of partially enter the container could have bad implications and can cause really severe vulnerabilities. So let's have a look at another solution.
So we've mentioned doing the copy from the actual host and also partially entering the container is problematic. And another implementation possibility is actually fully entering the container. The same way you would do a Docker exec or a kubectl exec, you could just get to all the namespaces of the container and simply not be able to see anything from the host. And that way, the previous vulnerability and other vulnerabilities we've seen would not be possible because you're simply namespaced inside the container and all the kernel protections are affecting you. And what could go wrong with this implementation? Well, now your helper binary is inside the container, and anyone running inside the container with more capabilities or same capabilities as yourself can control you. So that means any process basically inside the container can actually deal with what this binary you have does and its output and interact with it. And that means attackers with the same privileges as you could actually affect what you get outside the container from inside it. So instead of getting out files you were expecting, you might get something else. And that was actually a problem with Kubernetes. So let's take a step back and look at the Kubernetes implementation and see how it was done in Kubernetes. So kubectl cp is the command. And from its documentation, maybe a little bit small, but what it says is you need the tar file, the tar binary inside the container you want to copy from. So if you want to copy files from a container, it must have the tar binary inside it. Otherwise, the operation would just fail. And this implies heavily that the kubectl command simply executes the tar file from inside your container. And this was actually the implementation. To copy files out or inside the container, it uses the container tar from the bin tar, user bin tar, whatever it would have the tar file on. and it would archive the file the user requested and unpack them back at the host. And that leads to the main question of what if an attacker can now change or control the tar that kubectl is running. So basically, it could change the output of that tar binary process and deliver something to kubectl that may break it or simply not give the user what he wanted. Or worse of all, if there is some issue with the implementation of kubectl itself in the way it parses the output of this tar, then the attacker might be able to exploit it from inside the container. And this was some CVE that was found back in 2018 by some researcher. He tried to exploit kubectl, and he found out that there was a simple path traversal inside its implementation. So what is a path traversal? Basically, a tar file is just a list of files and directories. And if we have some file, which its name has some .. characters inside it, when kubectl would take this file and try to create it on the host file system, it would follow this full path. And by following, it means it would simply go back. And instead of copying to some remote dir that the user requested to copy to, it would go back to root and then copy the file to /temp directory. And that means that an attacker from inside the container could copy files he controlled, whatever files he created, to any place on the user system, which is also, as Yuval says, pretty bad. This was fixed by sanitizing the path, sanitizing the file names from inside the tar. So anytime kubectl would see .. it would simply eliminate it. And this vulnerability would not be able to be exploited again. But as you can imagine, this fix was pretty specific. It dealt only with the issue of path traversal. So if you might have had any other issues with the implementation of kubectl, this wouldn't have fixed them. They're still using the tar binary from inside the container, and it is still untrusted. We simply cannot trust any file that is running, any binary from inside the container, because it can be controlled by an attacker. So this led me about 1 year after seeing this vulnerability, I realized that Kubernetes is still using tar from inside containers, and I wanted to take a look at the implementation. And this led me to find some issue with symlinks. So instead of doing a regular path traversal, what I found was I could use symbolic links to get whatever file I want from my controlled tar to the user's system and recreate the previous issue. And how did I establish that? So I would, in my tar binary, it was always bring back the same tar, which had a file with a header that was a symbolic link to some critical path on the system that I wanted to override. And the second file in that tar would be some file that is in some allegedly directory. There is no real directory called sim on this tar file, but there was a symbolic link. And kubectl would simply go to that path, symbolic link, create this file, this critical path, and copy malicious file to the full critical path that I intended to get the file to. And the same previous issue was recreated, and I could exploit this to override any file I would want on the user system, which could be, if kubectl was run as root, could be really critical files, achieving code execution and whatnot. So I did disclose this issue to the Kubernetes and OpenShift security team, and they were really responsive and helpful in solving this really quickly. And there was a patch for this and an advisory. I did, in my original advisory that I sent, suggest to redesign this feature and basically not use a tar binary from inside the container. And I later realized this was actually something that has been suggested by Kubernetes developers in some GitHub issue. And there was an ongoing discussion on fixing this, but nobody has actually took the glove to change the implementation. So this was an issue for a while. And moving on some months later, the CNCF security audit you may have heard of that was invited to find bugs in the Kubernetes implementation actually realized the fix to this previous vulnerability was insufficient, and they found some games with which they could actually re-achieve the symlink escape. And you can see the number jumped from 6 to 9. Another vulnerability was found a few months after that with the same piece of code. Symlink restriction is simply not, it's not easy to implement, and there was yet another way to escape the restriction and copy files to the host. So there were about 3 CVEs for this issue. And hopefully now the implementation is much more secure. But again, the whole idea is that using something we don't transform inside the container is something we should really avoid. And I'm not the only one that has thought about this. And there was a Kubernetes enhancement proposal to actually either re-implement the CP command in Kubernetes or actually get rid of it. There is currently an huge ongoing discussion on what should be the future of the CP command. If you have some useful insight, you might want to join in. I think some of the users participating in this discussion are actually sitting in this room. So we don't know what is the right thing to do with Kubernetes, with kubectl, but we do have some insights looking at all these vulnerabilities to what we think may be good to do. Like, what is the baseline you want to follow when implementing a CP command from scratch now with any container engine. So the first thing is actually freezing the container processes before copying. So cgroups has some feature called cgroup freezer. You could simply use, like most container engines already use cgroups, so you could use that to actually pause the containers before doing the CP command, and you'd avoid any race issues like the Docker vulnerability that we've discussed earlier. And we do think you should enter the container, doing it with the current feature that the kernel provides us. Doing this from the host is still not so very safe. So you need to do all the copying from inside the container to avoid symlink issues, but you have to do it cautiously. So what does cautiously mean? It means get inside the container only with the truth. Only change the mount namespace, but you don't need to change everything else. To prevent someone from inside the container from interacting with you. This is actually what LXD does. And use nothing from the container. That means either on purpose, like using the tar binary from inside it, but also making sure it doesn't use any libraries from inside the container by accident, or simply making sure it is completely statically linked and doesn't call anything some attacker might have put inside the container. And with that, let's also mention some of the something that are being implemented in the kernel right now to actually solve these issues and allow us to do something even much better and stronger than that.
So there is actually a new syscall that is being built exactly to tackle this problem and a bunch of other problems that are related also to containers. So it's called OpenAT2. And what it does, it opens files and directory while restricting the path resolution. So you can open a file with multiple flags, but the one that interests us are lookup beneath and lookup in root. And what this syscall allows us to do is I can be a host process, and I can say I want to open this file inside the container, but I want all path resolution in the kernel to be restricted to the root of the container. So basically, symlinks can go outside of the container. So that's a really cool idea. And with that, we can go back to the simple implementation we saw at the start of Podwen, when we just try to access the file from the host, but use this new syscall. And we can avoid all of the complex solution with like entering the container that really caused a lot of trouble. So once that's implemented, we believe that in the future, there will be a much safer way to implement the CP command. And we hope that it will be implemented soon. We don't do it. It's a bunch of other smart guys. And that's it. Yeah. Thank you, guys.